Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover translational motion, and I broke this down into three main subject categories. The first being vectors, the second being acceleration, velocity, and position, and I'll get into their relationship between those three variables, and then also talk a little bit about their graphical representation and where you might see that on the MCAT. And then lastly, I'll talk about freefall and projectile motion. And translational motion will show up on one out of the four MCAT sections. That is going to be the physics chemistry section, obviously since this is a physics topic. And in terms of the physics material, this stuff is pretty high yield. I've seen a lot of velocity, acceleration stuff, freefall as well. So this is all good stuff. And so with that said, let's get into it. All right, so the first thing I want to do here is talk about what exactly translational motion is. And so translational motion is the motion of the center of mass of an object from one position to another relative to some fixed point. And so you can kind of think of this as like a car moving from point A to point B over a distance of a mile. Or say I hit a home run, and so, the ball travels from home plate all the way to, seat 596 past the outfield. And so this is in contrast to rotational motion. So rotational motion is when an object rotates around some internal axis. Think about this as like the Earth rotating around its central axis. And so just to summarize with an example, take football. So in football, you kick field goals, and these field goals are from a certain distance, let's say a 55-yard field goal. So when you kick that field goal, this ball is going to travel 55 yards from the point of view of, a player on the field, right? This is that fixed point of view. And that is translational motion. And during the time this kick is traveling 55 yards, it's rotating end over end. And so you can look at that football and you could analyze it in terms of its rotational motion, right? And that's just looking at how it's rotating around its central axis. And so why do these distinctions matter? Well, for translational motion versus rotational motion, you're going to have a different sets of equations, different variables. For instance, for translational motion, you'll have force, whereas for rotational motion, you'll have torque. And further, with rotational motion, you look at things like angular momentum, angular velocity, just these different quantities. And you can convert between both of them, but in terms of how they're analyzed a little bit differently. And so this podcast is really going to focus on translational motion because you're going to see a lot more of that on the MCAT. But just know that you also have rotational motion, and you can go through that before the MCAT just to kind of make sure that you've covered all those bases. But translational motion is definitely higher yield. All right, and so the first thing I want to get into in this podcast is vectors. And a vector describes a quantity that has both magnitude and direction. And this is in contrast to a scalar quantity, which only describes magnitude. So, for example, take time. So say, for instance, I woke up at 7:36 this morning. Well, this quantity is just as a magnitude, right? This is just a number. You can't have a directionality of time. You can't say, I woke up at 7:36 this morning, going forward in time. I guess, well, you can say that, but it doesn't really describe, time doesn't have a direction. Whereas if you say something like, wind is blowing 32 miles per hour out of the northeast, well, describes the velocity of the wind and the direction of the wind, and therefore it is a vector quantity. And further, vector quantities are typically depicted as an arrow, right? So they have an arrow and it points in the direction of this quantity, and the length of the arrow corresponds to the magnitude of this quantity. So the faster the wind is blowing, the longer that vector is. And one of the main applications of vectors is in drawing vector fields. And so I talked about this quite a bit when I talked about electric fields. And basically, an electric field represents the force a positively charged particle placed in that electric field would feel. So all these vectors in the electric field just represent forces basically at each of those points in space. So if you want to know more about that, go listen to the electromagnetism podcast. But for now, just have an understanding of what vectors represent in terms of having a direction and having a magnitude. And so there's three basic things you should know how to do involving vectors. The first of which is being able to draw them in simple physics diagrams. The second is being able to use them in different trigonometry problems, or being able to apply trigonometry to solve force problems or projectile problems like I'll talk about. The third is being able to do vector math. All right, so let's first talk about vector diagrams. And so this will make a little bit more sense when I start talking about falling objects and projectile motion and stuff. But in any problem involving some type of force or a bunch of forces, I really like to draw first a vector diagram. And so these are the things from freshman physics that your teacher probably drilled and was like, well, first draw a vector diagram. But I really do think it helps. And for me, I'm like a super visual learner. So I always like to sketch out, exactly what's going on in the problem first. Maybe it's like a 5-second sketch. It's super fast, but it just helps me kind of visualize the problem. And if you're somebody who is able to just kind of mentally look at a problem and kind of be able to figure it out without drawing it out, then this might not apply to you. But anyway, so you are able to draw a vector diagram using two different steps. So first, you draw the object in question as just a simple dot. And then next, you draw each of the forces acting on this object as a vector. And this sounds pretty trivial, but I would go ahead and practice a little bit. Make sure you're comfortable with drawing these diagrams and then using them to solve problems. The second thing that you're going to have to know how to do that involves vectors is trigonometry. So you might be given some problem where the MCAT says that you have a projectile launched, 30 degrees in reference to the horizontal at 100 miles an hour. And then you might be asked to calculate, the distance that object traveled, or the maximum height, or the time that was in the air, any number of variables. And so the first thing you're going to have to do in this problem, other than draw this vector diagram, is be able to perform pretty simple trigonometry calculations. And so what I really remember is the SOHCAHTOA mnemonic. And so this mnemonic helps us solve trigonometry problems by reminding us what sine, cosine, and tangent mean. So for instance, SO, which is SOH, means that sine of some angle is equal to the opposite side of the triangle divided by the hypotenuse of the triangle. Whereas cosine, or Ka part of this mnemonic, CAH, says that cosine of some angle is equal to the adjacent side of the triangle over the hypotenuse of the triangle. Then last we have TOA, which is TOA, and that stands for that the tangent of some angle is equal to the opposite side of the triangle over the adjacent side. And so what I did on the MCAT is whenever I was presented with a problem where I needed to use trigonometry, which are going to be a lot of the projectile problems, a lot of the force problems, I would write down just kind of the corner of my little scratch sheet, SOHCAHTOA. That way I could kind of look through and say, okay, do I need to use sine for this? Do I need to use cosine for this? Do I need to use tangent to be able to solve for the vector I'm trying to solve for, and then get the correct quantity, right? Because cosine of 30 degrees is not going to equal sine of 30 degrees. So if you mess up the trigonometry, you're going to get the problem wrong. And so my take-home message here is that if you don't know SOHCAHTOA, or you don't know how to do trigonometry, really focus on that and learn how to do that, because that kind of sets the foundation for a lot of these problems. All right, the last thing I want to talk about involving vectors is vector math. I'm going to talk about vector addition, subtraction, multiplication, and division. So first I want to start by saying that multiplying two vectors together, dividing two vectors together is actually pretty complicated and requires a bit more math than would show up on the MCAT. So I'm leaving those two out. But I will talk about what happens when you multiply a vector by a scalar. And in this case, all that's going to happen is that you are going to multiply or divide the vector's magnitude by that scalar. And so let me give you a quick example. So say that I am applying a 10 Newton force at a 35 degree angle in order to do an inclined bench press. Well, now say that I apply 10 times the same force to this bench press. How much force am I now applying to this inclined bench press? Well, all you have to do is multiply 10, which is the scalar value, by this vector force, which was 10 newtons. And now I'm outputting 100 newtons of force at this 35-degree angle. And so basically all that's happening is that this vector is getting bigger. It's getting longer, but its direction is remaining the same. All right, so that is multiplying or dividing by a scalar. Now let's talk about adding or subtracting two vectors together. And this gets a bit more complicated because now you have to take into account the directionality of each of the vectors that you're either adding or subtracting. And so all you have to do in order to add or subtract vectors is you first have to break them down into their component vectors. And so if you imagine with me a vector on a Cartesian graph pointing in the positive x, positive y direction, you can break that vector down into components by either projecting that vector onto the x and the y axis, so just kind of like shadowing it down and shadowing it across onto the x and y axis, or you can make it the hypotenuse of a triangle where the other sides of the triangle are parallel to the x and the y axis. And these other sides will be the x and y components of that vector. And of course, if you're given just, a force vector and said it's at a certain angle to the horizontal, you can use the SOHCAHTOA to then find the x and y components of that force vector. But pretend I just have this vector in a Cartesian graph so I know exactly what the x and the y components are. To add this vector to another vector, all I'm going to do is add the x component of one vector to the x component of another vector, and then I'm going to add the y component of one of the vectors to the y components of the other vector. In other words, all I'm doing is adding up the individual x components of the vectors and the individual y components of the vectors. And what that's going to give you is the x and y components of the resultant vector from that addition or that subtraction. And so then, of course, you can go back and you can find, the vector that has those components, which would be the final answer. So to briefly summarize, in order to add or subtract vectors, you need to first break them down into their component vectors, add up the individual components, which gives you the components, the x and y components of the resultant vector, and then you can use those components then to figure out what the vector would look like that is the sum or the difference of two vectors. So that's the numerical way to add vectors. You can also do this visually. You can make a parallelogram using the two vectors you're adding, and then the resultant vector is just going to be a vector that traces from one diagonal to the other of that parallelogram. The way I always learned to do it was you take these vectors that you're adding, you stack them together, so basically that it looks like one of the vectors is poking the other vector in the butt, and then from there you draw in a third vector that basically forms a triangle out of those three vectors. And that third vector that you draw in will be the resultant vector that results from these two vectors being added together. And obviously this is an audio medium, so some of you might be like, what the hell is he talking about? And as I always say, just go practice doing some of this. It's a very visual stuff, so if you really are not good at, drawing vector diagrams or doing vector addition, whatever, just go practice that. All right, the next thing that I want to talk about here is velocity, acceleration, and displacement. All right, so in this part of the podcast, I want to talk about velocity, acceleration, and displacement. And these are all vector quantities, meaning that they have direction and magnitude, which is what I just talked about. And to define these terms in the most basic way, displacement is a change in position, velocity is a change in displacement over time, and acceleration is a change in velocity over time. So just to give you a quick example, I rode my bike to work today, and it was about 3-ish miles. And so therefore, my displacement between work and my house was 3 miles, right? That was the displacement between the two. And it's important to note that this bike ride could have been more than 3 miles. And it is, right? Because the path is not just straight, right? It's not just the distance that the three-eyed raven would fly. It curves and it winds, and that would be known as the distance. And so distance is a scalar quantity, and that takes into account all the twists and turns it takes me to get to work. Whereas displacement just is worried about my first position in reference to my last position, which is 3 miles in this case. And in terms of the time it took me to bike to work, it took me about 20 minutes, and that was to go 3 miles. And so then you could say, on average, my velocity or my displacement over time was about 0.15 miles per minute, or about 9 miles per hour. And so again, this is the average velocity for the whole trip. And you can look at the velocity at very specific moments in time, and that's known as instantaneous velocity. And so, about 3/4 through my trip, I was biking, and the road that I was on was a little bit wet because it was morning, and this was the first time it rained in the morning, and it was just kind of cold and misty. But I'm going around this corner, and I just eat shit and land right on my knee. And this is definitely a true story, and I'm looking at my knee right now. It doesn't look great. But during that point of my trip, my instantaneous velocity was 0, right? Because I was down on the ground looking around to make sure that no one saw me. And therefore, at that point, my velocity was 0 because I wasn't even doing anything. But, the moment before that, I was going downhill. I was probably going 15 miles per hour. So you can look at velocity either as an average, being, total distance over total time, or you can look at instantaneous moments, which would be kind of like reading the odometer on your car, essentially, while you're driving. And I want to mention here that speed and velocity are two different things. So velocity is a vector quantity that has magnitude and direction, while speed is a scalar quantity that doesn't have direction. So the easiest way to see the difference between these two is by the following example. Say I run 1 lap around a track that's about 400 meters in a minute. What is my average speed and what is my average velocity? Well, my average speed is basically how fast I'm moving while I'm going around a track, and that's pretty easy. That's just 400 meters per minute. That's what I ran. What about my average velocity? Well, my average velocity is actually 0 meters per minute. In other words, my velocity is nothing. It's null, 0, zip. And that is because your displacement isn't changing from the beginning of your trip to the end of your trip, right? Or I guess this is me running around a track, but I start at the very start of the track, I run around, and I end at the very exact same point where I started. And therefore, your average velocity is actually 0 because your displacement is 0. Now, if this track were just to be straight and it was not a circle, then my average speed and my average velocity would be exactly the same thing. All right, let's give an example for acceleration now. So let's go back to the example of my bike. So when I fell off my bike, I was going about, let's say, 12 miles per hour. And then within a second, I was going 0 miles per hour because I had fallen. So my acceleration during this period, which is actually known as deceleration because I'm slowing down, is going to be negative 12 miles per hour in 1 second, or negative 12 divided by 1, which is going to be negative 12 miles per hour per second. And this doesn't really tell you too much because it's not like miles per hour or we see it every day, so we kind of know how to gauge it. But just know that this negative 12 miles per hour per second did not feel good. So just to quickly summarize, the rate of change in displacement over time is what's known as velocity, and then the rate and change of velocity over time is what's known as acceleration. And so I know what you're thinking then is, what is the rate and change of acceleration over time? And that is what's known, it is a physics term, and it's known as a jerk. And then now I know what you're wondering, what's the next one? So the rate of change of jerk over time is called snap, and the rate of change of snap over time is called crackle. And if you guessed that the rate of change of crackle over time is called pop, you are right. And I'm not making this up. This is literally physics terms for these different derivatives, essentially, of acceleration, jerk, snap, crackle, pop. Kind of weird, and that stuff is obviously not going to be on the MCAT, but I just thought it was kind of interesting. So the next thing I want to talk about is why understanding the relationship between velocity, acceleration, and displacement is important for the MCAT. And I've boiled this down to two different things. The first is in knowing how to do simple calculations involving acceleration, velocity, and displacement. And then the second is in understanding the relationship between the graphical representations of position, velocity, and time. And that should be a throwback to general physics where you were asked to convert, position versus time graph to velocity versus time or to acceleration versus time. And that is something I've seen show up on the MCAT, so I think you should know how to do it. All right, so for my first point, you need to be able to do simple calculations involving displacement, velocity, and acceleration. And these should be typically pretty easy. For example, say that you're given the distance between 2 points and given some time that it took an object to travel between these 2 points and asked to calculate the average velocity. Well, all you got to do is take this distance and divide it by the time that it took for the object to travel this distance, and that is average velocity. Or maybe you're asked something along the lines of the blood in your heart comes to a complete stop before it's ejected, reaching a maximum velocity of 10 meters per second, 1 second after it is ejected out of the heart through the left ventricle into the aorta. What is the acceleration of the blood? And the answer there is 10 meters per second per second. And so a lot of these calculations will be very simple. Where it gets a bit more difficult is when you're doing calculations involving acceleration and velocity in projectile motion. And I'll talk about that in a little bit later in the podcast. But just keep that in mind too. That's another place where you're going to see a lot of acceleration, velocity, position stuff come up. All right, on to my second point here, which is being able to understand the graphs of position, velocity, and acceleration, and being able to, number one, convert between those graphs, and being able to understand physically what's going on as you look at these graphs. So being able to say, okay, this person's moving forward here, now they're moving backwards, now they're accelerating, now they are going faster, now they're going slower, all those different things just by kind of looking at a graph. And just so we're clear, when I mention a graph being position versus time, position is on the y-axis, time is on the x-axis. And so I go through these problems on the principle that the slopes at each time in the position graph correspond to the values on the velocity graph, and then the slopes from the velocity graph at each point in time correspond to the values on the acceleration graph. And that's because that you're looking at rates of change, right? So velocity is simply the rate of change of position, whereas acceleration is simply the rate of change of velocity. So to convert then between these graphs, I just look at the slopes. So the slopes on the position graph will match up with the values on the velocity, and then velocity slopes match up with the values on the acceleration graph. So I work from that starting principle. And really the giveaway here is I look for places where the slopes are zero. So if I look at a position versus time graph and I see either a peak or a trough, those correspond to zero slope, right? Zero slope is just a horizontal line. That's no slope. So I look for places where there's no slope, and then I track those over to either the velocity or the acceleration if I'm looking at the velocity graph. But here I'm looking at position. So I'll track over those 0-point slopes over to the velocity versus time graph and look for where the lines of that graph cross zero, right? Because the velocity versus time graph should cross zero, which is going to be the x-axis, where there is zero slope on the position graph. And remember here for the MCAT, all you're trying to do is recognize, right? So you'll have all the graphs drawn out in front of you. It's just multiple choice. It'll just be picking the right one. So knowing the zeros is good. That helps me cross out a few of the potential graphs. The next thing I do is I look to see where slopes are negative. Where the slopes are negative, I know there will be negative values on the corresponding plot, right? So if I have a position graph and I see a negative slope, I'm thinking, okay, in my velocity graph, I should see a bunch of negative values, or it should be below the x-axis. And then that helps me narrow down more answers until I've crossed out 3 out of the potential 4 answers, and then I circle the answer that is not crossed out. So I really use kind of a method of elimination in order to then determine the correct velocity graph given position, or correct acceleration graph given velocity.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
And so what I'm going to do now is something that I haven't done before, but this is such a visual topic that I thought I'd do it. And that's going through an example using a picture from the internet. And so I have a link in the show notes to this picture that I'm looking at now. And it was created in GeoGebra by Tom Wilson and Marcus Hohenwarter. So thanks to them for creating this image. I'm just going to go through it, kind of break it down as an example. All right, so this picture is just a picture of 3 different plots. So you have position versus time, velocity versus time, and acceleration versus time. And so the first thing that you should notice here is that wherever you have 0 slope on the position versus time graph, you have an x-intercept on the velocity versus time. So you look at where you have either a maxima or a minima on the position versus time graph, which you have a maxima right at the beginning, and then like in the middle of the graph you have this minima. And so that's where the slopes are 0. And so then I can track that across to the velocity versus time graph, and I see, okay, sweet. The maxima is the first place where it intersects the x-axis, and then the other minima in this case is the second place where it intersects the x-axis. And so as I said earlier, the next thing that I check is I check to see where these slopes are positive and where the slopes are negative, and then I make sure that that correlates to the velocity versus time graph if I'm looking at position versus time. And in this case, it does. Wherever I see a negative slope or x is decreasing from left to right, I see a negative value for the velocity, right? We're below the x-axis that's shown. And if you want to pause the podcast and confirm this for yourself, feel free to do that. But I'm telling you, wherever the slope is decreasing in the position versus time graph, you have a negative value on the velocity versus time graph. And wherever you have a positive slope, you have a positive value on the velocity versus time graph. And these same principles apply when I'm trying to translate velocity versus time to acceleration versus time. I look at the slopes and then I transfer that over to the next plot. So take, for instance, the velocity versus time graph here that's in the middle. So I look and see, okay, where does this have a minima or where does this have a maxima? And when I say that, I mean that in terms of local. So I'm not just talking about where the graph is biggest versus where it's smallest. But in this case, it is where it's biggest and where it's smallest. So you look and you see this kind of spiky minima. And you can see, okay, that's where I know the slope is going to be 0. And look at that. In the acceleration versus time graph, it crosses the x-axis and is 0. The other place where I see 0 slope, or I see a maxima, which is this part where it comes up and it peaks off, that slope is also going to be 0, and that crosses the x-axis on the acceleration versus time plot. All right, so just to quickly summarize how I solve these problems. All right, so just to quickly recap what I just said. So basically, if I'm given the position versus time graph and I want to convert to velocity versus time, I look for the points where I have 0 slope on the position versus time plot, and I try to match that up with the velocity versus time, cross out some possible answers there, and then I look where the slopes are negative, where the slopes are positive, and I find my correct answer. And of course, you might be given velocity versus time and asked to determine the correct position versus time graph, and in that case, I just work backwards. I look at where the velocity versus time graph crosses 0, and I track that back and say, okay, there must be 0 slope at these points, and so forth. The last thing I want to mention in this segment is what exactly is going on physically in each of these plots. And it's the same thing, right? Because they're all corresponding to the same motion. And so I think the easiest way to think about this is to imagine somebody running back and forth in a straight line. So I'm sure you do this a lot, but just imagine yourself again doing this, going back and forth, running in a straight line. And so Let's assume that your initial starting point is a line that's drawn with chalk. So you're just standing on this line waiting to go. And additionally, assume that all the values in front of you are positive and all the values behind you are negative. So if you take a step forward, that is positive 1 foot. If you take 2 steps back from that position, you're now at minus 1 foot. So hopefully you got that imagined in your head. And now let's track your movement in terms of the position versus time graph that we've been shown. All right, so looking at the position versus time plot, right when you start walking forward, and you walk forward just a few steps until you hit this local maxima here, and that's the furthest forward you're going to get at this point. And then what happens is you're going to stop, and you're going to start reversing direction, and now you're walking backwards. And then this position versus time plot crosses the x-axis here, and at this point you are back at that starting line with the chalk that you drew. And you continue to walk backwards until you reach this local minima here, or this trough in the plot. And what happens there is you stop, you change directions, and you start walking forward. And you're still in the quote-unquote negative values, right? You're behind that line that you drew with the chalk, but now you're walking forwards and you're walking towards that line. And now, again, as you cross the x-axis, you cross that line with the chalk and you walk past it here, and you just keep walking and walking and walking and walking and walking. And now we can turn to our velocity versus time graph to see how fast we're moving during this little trip. So if we start again at this first point here, we can see that we have a positive velocity and it's kind of high. So let's say we're walking at this point. We're walking, but our velocity is decreasing. So we're walking, but we're walking slower and slower and slower until we stop. And we stop right at where the x-axis is 0. And again, this is where we turn around and start walking backwards. And now we have a negative velocity. And that doesn't necessarily mean we have negative speed, right? In fact, it doesn't mean we have negative speed, because it's impossible to be going in negative speed unless, of course, you're Eli Manning trying to escape the pocket. Now, what going in negative velocity means is that you're just traveling backwards, or your velocity is pointed in the negative direction. And remember, velocity is a vector quantity, so it's got magnitude and it's got direction. So anytime you see a negative velocity, don't think, well, that's impossible. Think instead, okay, that means they're traveling in the negative direction. All right, so where were we? We were at the point in which your velocity was 0, because now you're changing directions and you're turning around and starting to go backwards. And so at this point, your velocity becomes negative because you're walking backwards, and your velocity is going to get more and more negative until you reach this local minima here, or this little peak. And so what happens here is that your velocity is going to be at a minimum, but your speed is going to be pretty high, right? If I was to take the absolute value here, you would be traveling twice as fast as you were initially going forward. Of course, you're going backwards in this case, though. And once you reach this minima of velocity, you start to increase your velocity till again you reach 0 velocity. And this is where you turn around and start walking forward. And at this point, your velocity is in the forward direction, therefore it's positive. And it's going to start increasing and increasing and increasing until you reach a maxima, which is going to be the maximum velocity in this case. And if you were to take the absolute value again of your minimum velocity and compare that to your maximum velocity, you'd find that you're going the same speed at both of those points in time. So that's something to keep in mind. Now, lastly, let's talk about the acceleration versus time graph. So you can see pretty clearly here that the segments that make up this acceleration versus time graph are the slopes taken from the velocity versus time graph. And there's only one segment of the velocity versus time graph that has negative slope. That's that first little segment. And this shows us exactly where our acceleration is the highest and where it's the lowest. And so acceleration is the rate at which velocity is changing with time. And so the higher the acceleration, the faster you are increasing your velocity, and vice versa. And so you could imagine where you have high acceleration is where you're slamming on the gas pedal and you're going forward really fast, whereas low acceleration is where you're either decelerating or you are slamming on the gas pedal in the reverse direction, and accelerating in the negative direction. And you can see here that there's 2 places where the graph crosses the x-axis. And in those cases, you have constant velocity just for a moment at the first crossing, and then for, infinity time, depending on how far out this straight line goes in the velocity versus time graph. But when you have constant velocity, you have zero acceleration. All right, the next things I want to talk about are freefall and projectile motion. So the first thing I want to do here is distinguish projectile motion from freefall. So in freefall, all you have is a y component of motion, i.e. there is no horizontal motion. All that's going on is you're moving up or down, or whatever object you're looking at is moving up or down. This is something like dropping a bowling ball straight from your roof and having it fall straight down, right? There's no x component of movement, there's no horizontal movement. Whereas in projectile motion, you have both a horizontal and a vertical component of movement, right? You're shooting, let's say, the bowling ball now out of a cannon. So now it's traveling in the x direction horizontally, and it's also traveling in the y direction, which is vertical. And that's happening at the same time. And so if you remember back to physics, when you're dealing with projectile motion, you have to deal with the x and y components separately. And to do that, you have to do what I was talking about back in vectors, and you have to use SOHCAHTOA to split up this velocity vector now into a y component of velocity and an x component of velocity in order to deal with it and solve problems. All right, so let's talk first about free falling. And in terms of free fall, I have boiled this down to two different things to know. That's all you got to remember, two different things. The first is that you need to memorize the acceleration due to gravity, and that is going to be 10 meters per second squared. Don't try to use 9.8 meters per second squared. Doing calculations with 10 is a whole lot easier than trying to do calculations with 9.8. Number two, you have to memorize and know how to apply the equations that go along with free fall. And I will go through those and share some kind of tips and tricks and simplifications that I used. There are three equations to know for freefall, and these equations all use different combinations of the following variables: v, which is velocity, t, which is time, and d, which is vertical displacement or distance that the object falls. And all I've done to simplify these equations is I've plugged in the 10 for g, or for gravity, which is 10 meters per second squared, which is the acceleration due to gravity. So the first equation is that velocity is equal to negative 10 times t, which is time. The second equation is that d, or the distance fallen, is equal to negative 5 t squared. The last equation to know is that velocity squared, or v squared, is equal to negative 20 d. And you might be thinking to yourself, why are all those negative? Well, if we take down to be negative and up to be positive, which is typically the case, then acceleration due to gravity is going to be negative because its acceleration pointed downwards. And again, all I did to simplify these equations was I plugged in negative 10 for g in all these different kinematic equations, cut out the variables I didn't need, and now I'm left with a set of three equations that are very simple and easy to memorize. The next hardest part about these problems is deciding which equation to use to solve the problem. And so this depends upon which variables you are given in the problem and which you're trying to solve for. And this is pretty self-explanatory, right? So I have an equation that relates velocity and time. I have an equation that relates distance and time, and I have an equation that relates velocity and distance. So if I'm given velocity and want to solve for distance, I use that v squared is equal to negative 20d, and then I'll solve for d. Given velocity and needing to solve for time, I'll use the equation velocity is equal to negative 10t, and so forth. So it's pretty easy. You just got to remember these three equations and then know which one to use to solve for your unknown variable. In terms of concept, one thing that you should know for the MCAT is that an object's weight does not determine how fast it will fall, right? The variables that are at play here are distance and time in the air. In other words, an object's weight doesn't play in at all. So if I take a feather and I take a bowling ball and I put those in a vacuum so that there is no air resistance when I drop them, they actually will drop at the same rate and they'll hit the ground at the same time if they're dropped, of course, from the same height. On Earth, of course, we have air resistance. Our atmosphere is a little bit thicker than a vacuum. And because of this, a bowling ball and a feather dropped from the same height will definitely not hit the ground at the same time. It's also worth mentioning that in these physics problems, we tend to just ignore drag force or ignore air resistance. And so this implies that the only force a falling object feels is that of gravity, and the gravitational force exerts a constant acceleration. So what's going to happen to a falling object if we ignore air resistance? It's just going to continuously accelerate, and its velocity is just going to keep increasing until it hits the ground. In other words, if I drop an object from 3 miles above the surface of the Earth, it's going to be, thousands of miles per hour by the time it hits Earth. And we know this isn't the case, right? We know that this physics concept that we learned in freshman physics is kind of BS because there's such a thing as terminal velocity. And terminal velocity is when a falling object reaches a constant velocity or has zero acceleration. And this is when the drag force from air resistance is equal to the downward force of gravity. And for humans, just a fun fact, this is about 55 meters per second or 120 miles per hour. All right, so the last thing I want to talk about here is projectile motion. And projectile motion is quite a bit more annoying than freefall because you need to use some trig to split up the velocity you're given into its x and y components, take into account angle, and then also take into account the fact that this object is moving horizontally and vertically, and then solve for whatever you need to solve for. One thing that is similar between freefall and projectile motion is that once a projectile is fired, it feels only one force, and this is the same force that a free-falling object feels, which is the force of gravity. And to really show this, I'll give you an interesting example. So if I were to take a projectile and shoot it horizontally off a cliff, and take that same projectile and at the same time drop that object straight down the cliff, these two objects would actually hit the ground at the exact same time. And that makes sense, right? Because they're essentially being dropped from the same point. The only difference is one is experiencing some kind of horizontal motion at the same time it's experiencing that vertical motion. So you can kind of see that there's two different components to projectile motion. Really, this object is falling just like free fall, but it's got this other component of movement in the horizontal direction. In terms of what you need to know about projectile motion, I've broken this down into 3 categories. The first being you need to know how to break down an initial velocity into x and y components. The second is that you need to understand that the horizontal component of motion has constant velocity. And again, we are assuming that there's no air resistance here. So that x component or horizontal component has constant velocity. And the third is that you need to know, again, the equations to use and how to use them and memorize them. So let's talk about that first point. You need to know how to break down an initial velocity into x and y components. So typically you'll be given some initial velocity and you'll be told an angle from the ground that this projectile is fired. And really these equations are going to depend upon the reference angle that you have. So as I said, they will typically say the angle from the ground. But what if they say the angle from the vertical or the angle from a wall or something like that? These equations are going to change. But let's just call this angle theta, and we'll say it's the angle from the ground. Your x component of velocity will be equal to cosine theta times the initial velocity. And your y component of velocity will be sine theta times the initial velocity. And I just used the so and the ka from SOHCAHTOA in order to figure out these formulas. And of course, this is going to change if this is the angle from the vertical. And what I think you should do now is go see what these equations would be if I was to say that I fired a projectile theta degrees from the vertical line or 30 degrees from a wall or something like that. And so that is going to give you your x and y components of velocity. And now you're going to have to plug those into different equations in order to determine a bunch of different things, right? So we have a movement in the x direction, movement in the y direction, and we have the same set of kinematic equations that we can use, but you need to treat the x and y components of movement as completely separate from each other. And so there are 4 equations that you should know for projectile motion. The first 3 have to deal with motion in the vertical or y direction. The last one has to deal with motion in the x direction. The variables at play here are y, which is the height of the projectile, x, which is the distance the projectile has traveled. Then I have initial velocity in the y direction and final velocity in the y direction. And remember, your velocity is going to be changing with time when I fire that projectile in the y direction. And so this final velocity is just simply looking at the velocity at some point in time. And then I have the initial velocity in the x direction, and that is it. And so again, the first 3 equations deal with the y component, and these are that y is equal to the initial velocity in the y direction times t minus 5t squared. The second one is that the final velocity in the y direction is equal to the initial velocity in the y direction minus 10t. Then the last one is that the final velocity in the y direction squared is equal to the initial velocity in the y direction squared minus 20y. And again, I simplified these equations by plugging in the gravitational constant as negative 10 meters per second squared. And now there's only one equation to know in terms of the x or horizontal component, and that is that x, or the distance of the projectile, is equal to the initial velocity in the x direction times t. So let me just quickly summarize. So what you need to do is first split up the initial velocity you're given into an x and y component, and then plug that into whatever equation you need to solve for the variable that you are looking for. And real quickly, I want to mention one kind of extra credit equation. I've never seen it come up on the MCAT, but I really don't know what those crazy people like to add, so you never know. So the maximum height of a projectile is equal to the initial velocity squared times sine squared theta divided by 20. And the theta here is the angle between the ground and the projectile. So you might want to keep that on hand. I haven't ever seen that come up, but again, you never know. Before I go, I quickly want to do a little bit on air resistance and friction. So air resistance or drag is considered to be a type of friction. And friction is essentially a force that resists movement of an object. And you can think about this as like 2 solid objects on top of each other, sandpaper and a block of wood on an inclined plane. That adds a little bit of friction, helps that block stay put. Or you can think about it in terms of fluid surrounding an object. When you're swimming through water, it's hard because the fluid applies a drag force to you. And this drag force is proportional to 2 different things. Number 1, the velocity. So the faster an object is moving through some medium, the higher the drag force is going to be. And it is also proportional to the surface area of the surface that is in contact with the fluid. So if I take a piece of paper and I just drop it from my roof, it's kind of slowly going to float down, right? If I take that same piece of paper and I crumple it up and I drop it, it's going to go a lot faster. And that's because the surface area that is in contact with the air is decreased a bunch when I crumple up that piece of paper. So that's something to keep in mind. The faster an object is moving through a medium, the higher the drag force, and the bigger the surface area that's in contact with that medium, the higher the drag force. The second thing that I want to mention about air resistance and friction is that it is a non-conservative force. So what do I mean by non-conservative force? Well, I don't mean that this force is a Bernie bro. What I mean is that the work done by this force depends on the path taken. So this is in contrast to a lot of other forces that we talk about in physics that are path independent and are therefore conservative forces. So take, for example, a water slide, right? So in this water slide, there's a bunch of water and it is exhibiting a drag force backwards up the slide at me. Well, at the same time, I have a gravitational force that is pulling me down as I go down this slide. And so this water slide has a bunch of loops and turns and drops. But in the end, I go from a height of 27 meters up to an ending height of 0 meters. And for a conservative force, like gravitational force, for instance, that's all that matters, that I started at 27 meters and I ended at 0 meters. All the loops, all that other shit doesn't really matter in terms of the work that is done by that force. But for friction, it does. The longer this slide is and the more loops and all that stuff that it has, the more work friction is going to be able to do on me and the slower I'm going to be going in the end. So the takeaway message here is that for a non-conservative force, like friction, the path you take matters when we're talking about how much work is done by that force. So to quickly summarize those points, air resistance or drag is proportional to the velocity that an object is traveling in a medium, and also the object's surface area that is in contact with the medium. And then also air resistance, drag, and friction are non-conservative forces. And with that, we are done with the Translational Motion podcast. As always, thanks for listening to the podcast. I hope that it's helped you in your studies. If you felt like it helped you or you really like John Mayer, go leave us a review on iTunes. It helps us reach more students and helps us grow our popularity. I will be doing a CARS interview very shortly here. I think that will be released the week after this one, so stay tuned for that. Thanks.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.